In this slide, we have an example 14.3 for confidence intervals for regression. And if you remember, if in example 13.3, the parachutist velocity data below here, we use this for the regression to develop the following relationship between measurements and analytical model predictions. This model, we obtained it using the regression for analytical model regression results. And we also showed that this is actually a good fit with the measured results. And now we want to recomputer the regression, but we want to use the matrix approach to estimate the standard errors for the parameters. Then we employ these errors to develop two-sided 95% confidence intervals and use these to make a probabilistic statement regarding the goodness of fit. So we will again check the goodness of fit, but this time we will use confidence intervals to understand if it is good or not. To use the matrix form for the regression analysis, we actually need to write the data in matrix form first. So the Z matrices are basically the data, as you can see here. And the Y matrix is also the data. And we will use these by matrix transposition and multiplication to generate the normal equations. And if you remember, the normal equations were these. Actually, this Z times A equals Z transpose times Y. This Z transpose times Z actually is obtained by using this. This is just Z, this one, and transpose is a horizontal version of this. And this one, when you multiply them, you will obtain this result. A's are the unknowns because we are using a linear regression. It's just two unknowns. And Z transpose again, the transpose of this, times the Y values. When you multiply them, you will obtain these two only. And because this is a two-row matrix, when you have the transpose, you multiply the first row with this to obtain this, the second row and Y again to obtain this. You can do the calculations by yourself and you will see that you will get these matrices. So we use them. And this is actually same as the previous approach. In the previous approach, if you remember, we just used the linear regression for two equations and we calculated these summations actually to get the matrix results. So instead of that, now we are using just this matrix form. So these are two alternatives which gives the same results, actually same equation. If you go back to example 13.3 in chapter 13, you will see that we calculated these to get the regression, but now we are using these tables. It is the same as we said. And the matrix inversion can be used to obtain the slope and intercept. Basically, we will have the inverse of this, multiply this by that inverse to get only A. So this is the formulation for it, the inverse of Z transpose Z and this value here. So if we get the inverse of this, this is the value of the inverse. You can calculate the inverse. That's not very difficult. You can also use MATLAB to get inverse if you want to. And this is the Z transpose times Y values. When you multiply these, you will get these results. So this approach is using the inverse approach. But in example 13.3, in the previous chapter, we used these. And we didn't use the inverse of this, but we actually used elimination technique to be able to get A1. Then from there, we were getting A0. But here, it's a different concept using the inverse. And we determined the intercept and slope, meaning that the A0 and A1 values as the same as we determined before. You can see A1 is near 1 and A0 is minus 0.872. So this is near 0 as well. And we said that this, because these are 1 and 0 nearly, this is a good fit. We mentioned that. But of course, we can now have a better analysis of this using the confidence intervals. We will check that as well. But the equation is obtained same as before, like this. So these are just rounded values for 3 digits. And if we continue on the solution to be able to get the confidence intervals, first we calculate the standard error of estimate using this formulation, and basically from this you will obtain this value actually, and it can be used along with the diagonal elements of the matrix inverse to calculate the standard errors of the coefficients. In other words, we will have the inverse of the Z matrices like this. We already obtained this, and the diagonals are important here. So this first diagonal is this Z11 and the second diagonal is Z22. So we were calculating this S values for A0 and A1 using these root squares. We showed these while explaining the topic of confidence intervals. When you calculate them, so put this here, and SYX is this value, square of it. These are the S results. And now we need the T distribution. And for 95% confidence interval, alpha is 0.05 divided by 2, and minus 2 is actually 15 minus 2 is 13. So let's find the T distribution value for this using a statistical table or software. In the next slide, I will also show the statistical table. We can use that, or we can use software MATLAB as well, or Excel too. Let's check them in the next slide. In this slide, we have the T distribution table. You can see here, you can obtain such tables from internet, and this is the link that I obtained this. And you can go ahead and check. Actually, it's a longer version. These are the number of samples, by the way, and it goes up to a certain value, but I cut it on 15 because we have only n minus 2 equals 13. So we will use this 13th row to be able to get our T distribution value. And at the top, you see the significance level values, and we were using the 95% value, and we are using two-sided confidence interval. That's why here we need to focus on the two-sided one, this one. But if we consider one-sided, then this 95 becomes actually alpha divided by 2, and from there we can have 97.5%. So you can think of each case separately, but these will give the same result. So if you are going from one-sided for 95% confidence interval, you need to get the 97.5%. But if you are using the two-sided for 95% confidence interval, just use the 95% that we targeted. So then from here, 95% and 13th row, this 2.16 is our T value. We will use this in our confidence interval calculation. But before that, I want to show that if, let's say, we don't have the table, but we have Excel, Microsoft Excel software, over there we can also calculate this value using this code actually. So for a two-sided with 1 minus p, so p is our 0.05. If it's 95%, that means p basically is the 95%, and just so 0.95 actually. When you subtract it, it becomes 0.05. This is the alpha value, the significance value basically. And the Excel uses that along with the n-2 value, 13. And when you write this t in with equality with these values, it gives us the T distribution value for a significance level of 0.05 for 13 of n-2. And the result is the same, 2.16, as you can see. Of course, this table didn't show further digits after the 3, but here you can see more digits in Excel. Similarly, you can use MATLAB. In MATLAB, we have the same code actually, T in lower cases. In Excel, it's upper cases. Don't forget about it. But the difference is that we use the same 13, but the difference is here. For the significance level in MATLAB, it considers the one-sided version of the two-sided value. So if you have a 95% confidence interval that you are targeting two-sided results, in MATLAB, you need to think that, okay, I will write here the one-sided corresponding values. And you can see from this table that the one-sided value corresponds to 97.5. So we are writing 0.975. So not in percentages, but just in as the value. This is basically, you can think of that it's significance level divided by 2 and 1 minus significance level divided by 2. In summary, for Excel, we are using 1 minus p, which gives alpha. So this is alpha value. But in T inverse, it is opposite. We are using 1 minus alpha 2 here. So first calculate alpha, which is actually, if our confidence interval is said to be 95%, then it's like 0.95, subtracted from 1, 0.05, then divided by 2, 0.025, then subtracted from 1. It gives us this value. In MATLAB, you can use this, and it will give us the same result, because here you can see these two gives the same result anyway. You can use either of these three options. So this is the first option, this is the second, this is the third, and all of them will give the same result actually. And now we can calculate the confidence intervals. Let me erase this. The confidence interval formulation, if you remember, was this. For A0 and A1 we were getting the same values, and this is the formulation. So we calculated A0 and we calculated this S in the previous slide as well, and these T's are calculated here. If you write these all into these equations, L and A becomes plus and minus this value, and this is A0 anyway. So the result is this, and basically A0 will be between minus 2.4 to 0.6889. So it's a very large actually area for A0. And for A1 as well, you can use the same formulation, but just considering A1. And A1 becomes, again, this plus minus this value. So this is basically just multiplication of these, plus minus, you can see. And from here, we have an A1 value of 0.99 to 1.07. So it's a little bit narrower compared to A0 actually. And we can use these confidence intervals to show that, okay, our regression curve statistically will be in this area. And with 95% confidence, we can state these ranges. Let's continue interpreting this in the following slide. In this slide, we summarize the A0 values and A1 values we obtained from the confidence intervals. So A0 is in this range and A1 is in this range. And if you remember, the desired values for intercept A0 should be 0 to be able to have a good fit for this example, and A1 should be A1 actually. And we can see that 0 falls within this interval, it is in between, and A1 also falls within this interval. That means that we have a good fit actually, because these are within the intervals. Let's have some comments on slope A1. We have strong grounds for believing that the slope of the true regression line lies within the interval from A1 this to this value actually. We can interpret this value like this. And because A1 equals 1 falls within this interval, this is in this interval, we also have strong grounds for believing that the result supports the agreement between the measurements and the model. So this is basically a statistical description of this result, basically. Because this is in between this, statistically we are confident that our model is good, actually, according to the results. And this confidence is based on the 95% confidence, or 0.05 significance level. And let's comment the intercept A0, and it has the same statements, and because A0 equals 1 is in between these, so we have strong grounds that believing that the results support the agreement between the measurements and model for A0 as well. So you can make these conclusions based on these confidence intervals.